The next topic to consider are the units that we're using for integrals. Now we can think of integrals, if we're thinking about them as area, then when we think about the units, we can think about them as base times height. And since we have a unit for the base, unit times the height, we can multiply our units together when we're taking an integral if we think about our x units and our y units that are going into the integral. So if I have a time and velocity graph, the seconds will cancel out, showing me that my net change is going to be in meters. Or if I have a problem dealing with cost where I have X number of units and my function is a rate of my cost per unit, then again my units will cancel out, telling me that the antiderivative of that would just be the cost in dollars. Now in this next example, we're given a function for the acceleration. So it's important to remember the antiderivative of acceleration is going to give us velocity. Since they ask us how fast the car is going, they're asking about velocity. And so we're going to make an integral involving area here. But there are some things to pay attention to. We have an initial velocity of 5 meters, 5 miles per hour. So with that initial speed of 5, we want to start by saying we're going 5, we're going to add our net change, which is the integral. The integral being the acceleration there, which was 2.4. And we consider the units there. They say for 8 seconds, that means they're starting at 0 seconds and traveling for 8 seconds. We make that into an integral, and we can work it out, keeping the 5 in front. And so the notation we can use, make sure we keep this part in brackets when we take that antiderivative, going from 0 to 8. Now working that out, I'm going to take a shortcut to speed it up, it will come to 81.8. If we consider the units here, we can see that we're talking about velocity is in miles per hour, and so we can just go ahead and say this is velocity, and that's therefore in miles per hour. The second question, though, is dealing with distance. How far did it travel? So they don't explicitly say that, but they want a total distance here. Now really that should be then an absolute value of our integral. Now one thing that we need to pay attention, I'm sorry I got a little ahead, if it's distance, we're not using the acceleration anymore. Notice what I put in here. I put in my velocity function. Now we did find the antiderivative up here, but I've added something else here. I've added a 5. Where did that 5 come from? Well, my antiderivative should have been 1.2 t squared plus a constant. The constant, when we're dealing with this kind of problem, is always our initial point. We have an initial velocity of 5. So if we're starting at 5, then we're just adding that wherever we're at. And so for my velocity formula, we're going to have that plus 5 in there. And putting this into my calculator, it will come to 244.8. But what units is this? If we pay attention, we had, first of all, velocity inside of our integral. Okay, so here, right here, miles per hour from velocity. And we need to multiply that by the units that we're using for x. These are in seconds. So we have mile per hour seconds. That doesn't really make sense. We don't really use that unit. It's inconvenient for us to use a unit like that. So if I think about these units and I want to get them into something that's more useful, I want to somehow cancel out the hours and seconds here. What I'm going to do is think about how hours corresponds to seconds, and I know that 1 hour corresponds to 3,600 seconds. Looking at those units, I can now see how the hours will cancel out, the seconds will cancel out, and so basically if I take my 244.8 and I divide that by 3,600, then I'm going to get about 0.068. I'm left with a convenient unit of miles, which is also a unit of distance, which makes sense to us. And so our answer would be a very small decimal, but it makes sense because we've only gone for 8 seconds. for this next question, I want to focus on the units specifically. We have a rate of change here, which is given to us in millions of bushels per year. And so I could write that unit, millions of bushels, per year. If we look at the units then that are being used for our integral here, going from 2 to 3, these are measured in years. So when I multiply these units, the years cancel out, leaving me with a unit of millions of bushels. Now, this is the last question we'll look at today. We're wanting to know the difference between position, where the particle is at the end of the trip, versus the total distance traveled. So again, we've got some positives, some negatives that are going to be canceling each other out. For part A, we're looking for a net change because we have an initial starting point. We're starting at 2, and then we make some change as we go. Looking at our graph, we need to think about our change in terms of area, where we have a +1. Our next part is a -1, then a +1, and then another -1. Notice that net change is coming out to 0. So basically, we started where we were, we moved back and forth for a while, but in the end, we're back at the same position that we started at, the position where x is equal to 2. The next one is asking about the total distance. With the total distance traveled, we don't care where we started. We also care about how tired we are, so we need to make this into an absolute value sort of thing, where we're going to flip all of these over. Think about it as an absolute value of the function, so our total distance there is 4.